My goal in this tutorial is to give you a broad understanding of how inductors work. Also, we will not go into the deep details of the physics of electronic components or equivalent models, but we will go into the function of inductors enough to understand how inductors can be used. In this video, I have reviewed the most common inductors. In this video, we will see that the inductor is an electrical component used to introduce inductance into a circuit which opposes the change of current flow, both magnitude and direction, and that even a straight piece of conductive wire can have some amount of inductance in it. Inductor is a passive electronic component which stores energy in the form of a magnetic field. In simple words, an inductor consists of just a wire loop or coil that is used to control electric spikes by temporarily storing energy and then releasing it back into the circuit through an electromagnetic field. In my previous videos on electromagnetism, we saw that when an electric current flows through a wire conductor, a magnetic flux is developed around that conductor. This effect produces a relationship between the direction of the magnetic flux, which is circulating around the conductor, and the direction of the current flowing through the same conductor. This results in a relationship between current and magnetic flux direction called Fleming's right-hand rule. But there is also another important property relating to a wound coil that also exists, which is that a secondary voltage is induced into the same coil by the movement of the magnetic flux as it opposes or resists any changes in the electrical current flowing in. In its most basic form, an inductor is nothing more than a coil of wire wound around a central core. For most coils, the current flowing through the coil produces a magnetic flux around it that is proportional to this flow of electrical current. Inductors are formed with wire tightly wrapped around a solid central core, which can be either a straight cylindrical rod or a continuous loop or ring to concentrate their magnetic flux. In circuit diagrams, an inductor is represented by a coil or loops. It typically looks like a series of several closely spaced loops or a coil of wire, often with two terminals. The ends of the symbol normally indicate the terminals where an inductor can be connected to a circuit. Different types of inductors. The different types of inductors include the following. Iron core inductors are made of iron and are normally used in high-power inductors, but they are limited in high-frequency capacity. They are used in places where low-space inductors are required because, being low-space inductors, they have high inductance value when compared to air core conductors. Also, there is a significant energy loss in the process. These inductors are widely used in audio equipment. Air core inductor. Air core inductors are hollow and are normally used in applications where the level of inductance requirement is very low. The fact that no core is used ensures there are no losses within the core and the coil is supported by the air. These types of inductors are effective in high-frequency settings. The core of these conductors is made up of plastic or ceramic, and so they are also known as ceramic conductors. Iron powder inductor. An iron powder inductor is an inductor that uses compressed iron powder in its core. This core material makes it possible to create a magnetic field around the inductor so that when an electric current runs through it, energy is stored in the form of a magnetic field. These inductors have the ability to give relatively high values of inductance for their size and are well suited for all types of electronic products where space and cost need consideration. These inductors are also used in power supplies, filters, and radio frequency circuits. Ferrite core inductor. Ferrite core inductors use a rod or core made from a ferric material. The two main components of these inductors are the ferrite core and the winding. The most common material used in ferrite core inductors is ferromagnetic material, which increases the formation of a magnetic field, thus providing a higher inductance value. Ferrite core inductors are further classified into two types, namely soft ferrites and hard ferrites. Choke. A choke inductor, more commonly called a choke, is an electrical component used chiefly for choking off or blocking alternating current, AC, while allowing direct current, DC, to pass with relatively little resistance. This sort of inductor has a high impedance to AC signals, so it effectively filters or isolates them from circuits. Chokes are most commonly used in electronic circuits for filtering and noise suppression, as well as to separate AC and DC signals. Inductor is made of a wire whose property is inductance, i.e. it opposes the flow of current. The inductance of the wire increases when the number of turns is increased. Inductance is represented by the alphabet L, and it is measured in Henry. The formula of inductance can be given by the ratio of flux and the current in the circuit. Inductance is directly proportional to the number of turns in the coil. It also depends on other things such as the radius of the coil and the type of material around which the coil is wound. Unit of inductance is 1 Henry, H. The unit is symbolized by the letter H. Because the Henry is a relatively large unit of inductance in its own right, for the smaller inductors subunits of the Henry are used to denote its value. An inductor coil has a central core area, A, with a constant number of turns of wire per unit length, L. So if a coil of N turns is linked by an amount of magnetic flux, then the coil has a flux linkage of an any current, I, that flows through the coil will produce an induced magnetic flux in the opposite direction to the flow of current. Then according to Faraday's law, any change in this magnetic flux linkage produces a self-induced voltage in the single coil of a time-varying magnetic field induces a voltage that is proportional to the rate of change of the current, producing it with a positive value indicating an increase in EMF and a negative value indicating a decrease in EMF. The equation relating this self-induced voltage, current and inductance can be found by substituting the mu N2A Hever division sign L with L denoting the constant of proportionality called the inductance of the coil. The relation between the flux in the inductor and the current flowing through the inductor is given as an inductor consists of a coil of conducting wire, this then reduces the previous equation to give the self-induced EMF, sometimes called the back EMF induced in the coil too. So from this equation, we can say that the self-induced EMF equals inductance times the rate of current change, and a circuit has an inductance of 1 Henry will have an EMF of 1 volt induced in the circuit when the current flowing through the circuit changes at a rate of 1 ampere per second. With a steady-state DC current flowing through the inductor and therefore zero induced voltage across it, the inductor acts as a short circuit equal to a piece of wire, or at the very least a very low value resistance. In other words, the opposition to the flow of current offered by an inductor is very different between AC and DC circuits. The time constant of an inductor. We now know that the current cannot change instantaneously in an inductor because for this to occur, the current would need to change by a finite amount in zero time, which would result in the rate of current change being infinite, making the induced EMF infinite as well, and infinite voltages do not exist. However, if the current flowing through an inductor changes very rapidly, such as with the operation of a switch, high voltages can be induced across the inductor's coil. Consider the circuit of a pure inductor. With the switch open, no current flows through the inductor coil. As no current flows through the inductor, the rate of change of current, di/dt, in the coil will be zero. If the rate of change of current is zero, there is no self-induced back EMF within the inductor coil. If we now close the switch, t equals 0. A current will flow through the circuit and slowly rise to its maximum value at a rate determined by the inductance of the inductor. This rate of current flowing through the inductor multiplied by the inductor's inductance in henries results in some fixed value self-induced EMF being produced across the coil as determined by Faraday's equation. This self-induced EMF across the inductor's coil, VL, fights against the applied voltage until the current reaches its maximum value and a steady-state condition is reached. The current which now flows through the coil is determined only by the DC, or pure resistance of the coil's windings, as the reactance value of the coil has decreased to 0 because the rate of change of current is 0 in a steady-state condition. In other words, in a real coil only the coil's DC resistance exists to oppose the flow of current through itself. Likewise, if switch is opened, the current flowing through the coil will start to fall, but the inductor will again fight against this change and try to keep the current flowing at its previous value by inducing another voltage in the other direction. The slope of the fall will be negative and related to the inductance of the coil as shown. How much induced voltage will be produced by the inductor depends upon the rate of current change. In our tutorial about electromagnetic induction, Lenz's law stated that the direction of an induced EMF is such that it will always opposes the change that is causing it. In other words, an induced EMF will always oppose the motion or change which started the induced EMF in the first place. So with a decreasing current the voltage polarity will be acting as a source, and with an increasing current the voltage polarity will be acting as a load. So for the same rate of current change through the coil, either increasing or decreasing, the magnitude of the induced EMF will be the same. A steady-state direct current of 4 ampere passes through a solenoid coil of 0.5 Henry. What would be the average back EMF voltage induced in the coil if the switch in the above circuit was opened for 10 milliseconds and the current flowing through the coil dropped to 0 ampere? We know that an inductor in a circuit opposes the flow of current, I, through it because the flow of this current induces an EMF that opposes it, Lenz's law. Then work has to be done by the external battery source in order to keep the current flowing against this induced EMF. The instantaneous power used in forcing the current, i.e. against this self-induced EMF. Power in a circuit is given as P equals V times I. Therefore, an ideal inductor has no resistance, only inductance, so R equals 0 ohm, and therefore no power is dissipated within the coil, so we can say that an ideal inductor has zero power loss. When power flows into an inductor, energy is stored in its magnetic field. When the current flowing through the inductor is increasing and dI/dt becomes greater than 0, the instantaneous power in the circuit must also be greater than 0, positive, which means that energy is being stored in the inductor. Likewise, if the current through the inductor is decreasing and dI/dt is less than 0, then the instantaneous power must also be less than 0, negative, which means that the inductor is returning energy back into the circuit. Then by integrating the equation for power above, the total magnetic energy, which is always positive, being stored in the inductor. The energy is actually being stored within the magnetic field that surrounds the inductor by the current flowing through it. In an ideal inductor that has no resistance or capacitance, as the current increases, energy flows into the inductor and is stored there within its magnetic field without loss. It is not released until the current decreases and the magnetic field collapses. Then in an alternating current, AC circuit, an inductor is constantly storing and delivering energy on each and every cycle. If the current flowing through the inductor is constant as in a DC circuit, then there is no change in the stored energy as So inductors can be defined as passive components, as they can both store and deliver energy to the circuit, but they cannot generate energy. An ideal inductor is classed as lossless, meaning that it can store energy indefinitely as no energy is lost. However, real inductors will always have some resistance associated with the windings of the coil, and whenever current flows through a resistance, energy is lost in the form of heat due to Ohm's law, regardless of whether the current is alternating or constant. Then the primary use for inductors is in filtering circuits, resonance circuits, and for current limiting. An inductor can be used in circuits to block or reshape alternating current or a range of sinusoidal frequencies, and in this role an inductor can be used as tune for simple radio receiver or various types of oscillators. It can also protect sensitive equipment from destructive voltage spikes and high inrush currents. Inductors in parallel form. Inductors in parallel are the network of inductors that are connected together with the same two nodes in a circuit. This setup is similar to the connections of resistors in parallel. When connected in parallel, the voltage across each inductor remains the same. However, the current in each inductor will be different. The maximum opposing inductor will receive the minimum current. The total inductance of all the inductors connected in parallel will always be less than the individual inductance present in the circuit. The total current in the circuit is the sum of current in each inductor. The total inductance in the circuit increases or decreases according to the amount of magnetic coupling between the coils. The total inductance in the circuit where inductors are connected in parallel is given by the formula. 3 inductors of 60 mH, 120 mH, and 75 mH are connected together in a parallel combination with no mutual inductance between them. Calculate the total inductance of the parallel combination. Two inductors whose self-inductances are of 75 mH and 55 mH respectively are connected together in parallel aiding. Their mutual inductance is given as 22.5 mH. Calculate the total inductance of the parallel combination. Inductors in series. The inductor in series refers to the network of inductors connected end to end so that there is only one path for the flow of electric current. The current flowing in each inductor remains the same, but the voltage drop in each inductor is different. When inductors are put together end to end in an electrical circuit, their individual amount of inductance adds up to make one total degree of induction. This means that all the inductors connecting together in a series make a stronger impact than any one inductor alone. Total inductance in the circuit where inductors are connected in series is given by the formula. We know that in series the current is equal in each branch. That is, total voltage in the circuit is given by we know that the formula for voltage across an inductor is given by we can write but here. So, the equation reduces to hence, the total inductance is given. To calculate the total inductance of the circuit, the total inductance LT will be calculate the equivalent inductance of the inductive circuit. Energy stored in an inductor. When electric current flows through an inductor, electrical energy is stored in it. An inductor stores this electrical energy in the form of magnetic energy. The amount of electrical energy an inductor can store depends on its inductance and the magnitude of the electric current flowing through it. This formula can determine the electrical energy stored by an inductor. Impedance of an inductor. Impedance of an inductor is a measure of the resistance offered by the alternating current, AC, passing through a circuit. In simple words, impedance can be referred to as the opposition to the current passing in a circuit. Usually, it is denoted by Z. The standard measure for inductance is ohm. The formula for an inductor's impedance is stores energy in a magnetic field when electric current flows through it. It typically consists of a conductor, such as a wire, wound into a coil. When current flows through the coil of an inductor, a magnetic field is generated around it. This field stores energy. If the current changes, the magnetic field changes, inducing a voltage opposite to the change in current, based on Lenz's law. The power factor for a pure inductor value is always 0. Self-induction is a type of induction in which a coil tends to resist changes in current in itself. When changing current in one coil induces an EMF in the other coil, the phenomenon is called mutual induction. The strength of the induced EMF depends on the mutual inductance of the pair of coils. An EMF is induced in a circuit when there is a change in the magnetic flux passing through it. An inductor blocks AC because it resists changes in current flow. For DC, once the initial electromagnetic field is built up, there is no change in current, so the inductor behaves almost like a short circuit, allowing DC to pass through with minimal resistance. Several factors influence the inductance of a coil. The number of turns in the coil. The material of the core, ferromagnetic materials increase inductance. The shape and size of the coil. The presence of a core material within the coil. There are various types of inductors, each suited for different applications. Air core inductors, which do not use a magnetic core. Iron core inductors, which have a ferromagnetic core to enhance the magnetic field. Toroidal inductors, which are wound on a donut-shaped core. Ferrite beads, used in electronic circuits to suppress high-frequency noise. In AC circuits, inductors are used to block higher frequencies while allowing lower frequencies to pass. They are commonly used in filters, like those in audio and radio frequency applications.
Time